Meet the lock-in amplifiers that measure at microwave frequencies. Hi, I'm Jan, and we at Zurich Instruments are really excited, and I hope you are as well, about us introducing two new models to our lock-in amplifier lineup, the SHFLI and the GHFLI. Zurich Instruments and lock-in amplifier for many people has almost developed into synonyms. In fact, Zurich Instruments was founded with the vision to provide the best lock-in amplifiers to the scientific and engineering communities. And ever since, we have been amazed and excited what kind of measurements can be carried out by our customers over time. By introducing the HFLI, we have forever changed how lock-ins are perceived in the market. Parallel measurements, the integration of a large tool set, and also the no knobs and button concept, instead computer control, are now the state of the art. The UHFLI, a few years later, pioneered a new frequency range up to 600 MHz, and only shortly thereafter added boxcar averaging and arbitrary waveform generation to the mix what a lock-in amplifier today can do. And our so far latest model, the MFLI, is available in two versions, 500 kHz and 5 MHz. Now, every introduction of a new instrument also makes new applications possible. For instance, fast multi-component spectroscopy, qubit characterization, the characterization and control of resonators and oscillators, fast impedance analysis, and so on. And now it's time to push the frequency limits for lock-in amplifiers once again. So introducing our new models, the GHFLI and the SHFLI, we actually achieve an extension of more than a factor of 10. So they measure from DC to 1.8 GHz and 8.5 GHz respectively, so well in the microwave domain. Measurement at microwave frequencies are typically the privilege of fast oscilloscope, spectrum analyzers, and signal generators. But what if you could have all of this functionality in a single instrument and then some? Which applications would actually benefit most, progress faster, or even get enabled by this technology? We have some ideas, of course, but we are very curious to explore that further with you. Now, what we know for sure is what kind of new features we bring to the microwave domain, be it analog outputs with offsets and scaling for system integration, the integration of PLL and PID controllers, and of course, multiple phase measurements at multiple frequencies at the same time. All of these new features are, of course, available through our instrumentation software, Lab 1. Now, more details will be provided by our product managers, Quanch and Paolo. They will give an introduction to the SHFLI and GHFLI and will be happy to take your questions and further discussion after that. So please make use of the Q&A box below, and I hope you enjoy the further presentation. Over to you, Quanch.
Thank you, Jan, for the nice introduction, and also welcome from our side. I'm Quanch, and I'm together with Paolo to discuss our new lock-in amplifiers, GHFLI and SHFLI. I have a couple of questions to direct him so that we understand the two instruments better. So, Paolo, what pushed the Zurich Instruments to introduce these two lean lock-in amplifiers that go beyond gigahertz frequencies?
Yeah, in the past years, we've seen a clear trend in some applications, in some research. Something like quantum computing, but also NEMS and optomechanics and spintronics and more. All of these tend to move towards higher frequencies and enter into the gigahertz range. And therefore, we get requests from some customers asking for a lock-in amplifier that goes beyond the 600 MHz limit of our UHFLI lock-in amplifier. So effectively, we decided then with these two instruments to bring the benefits of lock-in amplifiers to the microwave. And we decided to bring out two instruments instead of just one to better match, better fit the needs of the different applications of our customers.
So you mentioned the trend in research towards higher frequencies, but clearly these applications already exist. What the users are working with at the moment?
All right. Yeah, currently two main types of instruments are used for this kind of research. Spectrum analyzers and VNAs are workhorses in these fields, and they're invaluable. They're really powerful, but they're limited in certain aspects, and these limitations makes them not ideal to complete the measurements for these applications. For instance, spectrum analyzers, they are fast in their measurements and they're easy to set up, but their noise suppression is somewhat limited. And there is no phase information, and also they usually don't have a signal generator, which means that they cannot do a full characterization of a device, transfer function of a device directly without a signal generator on their side. VNAs, on the other hand, are quite different in their limitations and their strengths. So they are very good at noise rejection. They are also highly calibrated for very good accuracy, but in general, they cannot measure external signals. They don't, therefore, they are not able to track frequencies, and they don't provide the ability to track resonances. So all of these limitations are sort of not there with lock-in amplifiers. Lock-in amplifiers sit in the middle and bring the best of both worlds. So you have a very high flexibility in deciding whether you want to measure fast or you want to suppress noise by choosing the low-pass filter bandwidth in your measurement. And intrinsically, you get the phase information. Lock-in amplification is a phase-sensitive kind of detection, so you get phase. And since you are locked to a certain external signal, you can measure external signals, and you can also track their frequencies. You get that information as well. And then most lock-in amplifiers, if not all, also provide auxiliary outputs, which means that now your measured values can also be transferred back into the analog domain so that they can be fed to other instruments in your setup through analog domain channels.
So the lock-in amplifiers are also simplifying actually for the users who currently need higher frequency access. Yeah. But beyond that, what are the other benefits these two lock-in amplifiers offer to the user?
Right. In addition to the benefits of general lock-in amplifiers, we have used the same philosophy that we've used to develop all of our previous lock-in amplifiers. So we try to introduce as much functionality and as much parallelism as possible into each of our instruments. So, for instance, like our UHFLI and HF2LI, they have two channels. These two channels operate as two independent lock-in amplifiers in one box. So each of the two has two channels. Each channel has 4 demodulators and 1 signal generator. So you can measure up to 4 frequency components in parallel per channel. And this allows for multi-frequency, multi-harmonics analysis. Plus, we are going to provide or offer upgrade options in the future that, again, will be familiar to our customers, but things like multi-frequency, so that you can really measure up to actually 8 frequency components at the same time at arbitrary frequencies, or things like the PID controllers. In addition, we've spent a lot of effort to design our analog front ends as well as possible, so that we can provide extremely low input noise, as low as 3 to 2.5 nanovolts per square root hertz, and overall, over all the frequency range, the noise stays extremely low. Noise, of course, is also something that we are suppressing with a lock-in amplifier. So the modulator section is then very important, and one important parameter is the time constant or bandwidth of the low-pass filter. And here you have a very broad range going from 14 nanoseconds all the way up to 21 seconds. And this means that you have a very big range of choices. If you want to measure extremely fast events, even below 100 nanoseconds long, you have these 14 nanoseconds. And this is also very important when you want to do fast imaging, fast raster imaging. On the other hand, if you have a small signal and a lot of noise, the 21 seconds will allow you to really integrate for a long time, really suppress your noise and extract your signal from the background. I mentioned the auxiliary outputs. These are extremely important for lock-in amplifiers. And in this case, we offer 8, not just 4 like in some of our other lock-in amplifiers. And this allows us to provide 2 different kinds of auxiliary outputs. We have the high-speed ones that gives you the possibility to really get the 14 nanoseconds measurements out. And on the other hand, you have also the high precisions that are much smaller in bandwidth, but really gives you the 18 bits that are vital when you want to do very precise work and measure and be able to see very small steps in your measurements. And this is great if you're integrating your lock-in amplifier into a setup, but since we already have all the measurements in a digital form inside and we are controlling everything from a computer, we also provide a high-speed digital channel to get your data from the instrument to the computer so that you can save your data or you can visualize it into the Lab 1 user interface.
So the hardware offers very high quality signal quality, and also with the different kinds of channels and the channel density, they're quite flexible instruments to address various applications.
Exactly.
But clearly there is no knobs or screens to look at the signals, and you already mentioned that the signals are transferred to computer very efficiently. So how things work on the software side then?
So software, we provide the same software suite that we provide with our other lock-in amplifiers, the Lab 1 software that contains APIs, but also the graphical user interface. And it's not just a software package, it's also a tool set. So we provide additional functionality through Lab 1. We have tools like the oscilloscope that allows you to characterize and control your signals at the input at all times, both in the time and in the frequency domain. We have the sweeper, which is a very powerful tool that allows you to very easily set up sweeps of parameters such as the frequency, but also amplitudes, phases, and so on. And it makes makes setting up certain measurements extremely easy. And not only you can sweep different parameters, but you can also measure different parameters from the demodulators, such as the amplitude, the phase, but also X and Y. And you can measure multiple of these parameters at the same time from multiple demodulators, and you can construct a better picture of your system under test. We also provide many different ways of acquire data and save data. So from plots that you can save as an image to data in just ASCII formats or MATLAB, HDF5, and so on. Mm-hmm. All of this functionality is available in parallel, so you can run all 8 demodulators together with the sweeper, together with the oscilloscope. There is no limit. Everything is running on the instrument. Everything runs in parallel. You don't have to choose what you want to do.
It's great then to be able to see the different aspects of the signal at the same time, like looking at the frequency response while checking the spectrum of the signal, etc., and then be able to save the data in different forms. Yeah. But this happens, of course, in the user interface. How about the users who need to integrate the instruments to their existing setup or automate things?
Right. So all of the functionality that I mentioned and more that I didn't mention is available in the APIs. So that it's very easy for our customers to take the instrument and integrate fully what they need into their code. We provide APIs for MATLAB, LabVIEW, Python, C, and .NET.
Okay, so there's also a lot of flexibility there, and people can do this easily. Earlier you mentioned upgrade options. Can you explain a bit more there? What is coming next?
Sure, absolutely. Like, again, our other lock-in amplifiers, we provide a whole suite of upgrade options for the GHFLI and the SHFLI, and all of these can be purchased together with the instrument, but also at a later stage and easily upgraded in the field without any need to return the instrument or recalibration. Everything can be done by the customer themselves. And we have a full roadmap of upgrade options coming. For 2023, we are planning to release the multi-frequency option, very popular, the AM, FM modulation option, and the PID option, again, a very important option for our customers.
I see. So there's quite a lot of down in the line to expect.
Absolutely.
To improve the capabilities of the two instruments. But so far we addressed the two instruments together, the SHFLI and GHFLI. Obviously there are two different instruments, but what are these differences actually?
Right. Well, obviously they are a bit different in size. The GHFLI is slightly more compact, the SHFLI. And also another obvious difference is the frequency range. So the GHFLI has a frequency range from DC to 1.8 gigahertz, while the SHFLI has a frequency range from DC to 8.5 gigahertz. And behind the scenes, they work a little bit differently. The GHFLI is the direct digitization instrument, so it accesses all the 1.8 gigahertz bandwidth at all times, whereas the SHFLI is a frequency up and down conversion instrument, so it has front ends both at the input and at the output to mix the frequency up and down, so that effectively it works with a 1 gigahertz wide measurement window that the user can then set to their frequency of interest, and within that they can set their demodulators. And the two channels, as I mentioned before, are completely independent, so even in this can be completely independent. You can set the two windows independently, one looking at 6 gigahertz, for instance, the other one measuring 4.5 or even down to DC.
Okay, so the main difference is actually in the frequency range that they can cover, and they actually complement each other for various applications where the different frequency ranges are needed.
Absolutely, absolutely. Yeah. And yeah, as I said, how it's implemented is a bit different. The SHFLIs may be slightly different from the lock-in amplifiers that you find normally on the market. So you will see, or you will see more about this in the demo later on.
Yeah. This actually brings us to a very nice topic. Thank you, Paolo, for answering these questions. I hope he was also able to answer some of the questions you have in mind, but please keep asking these questions. We will go to now a live Q&A section to answer them. And after that, we will still be around and continue with a demo of the instruments. Please stick around then as well. Thank you. We can now do a deep dive into the instruments and their functionality. Let's start by connecting this resonator to the instrument. It's a pillbox resonator which has resonance modes from 3 GHz to 8.2 GHz. Due to its frequency range, I will use the SHFLI lock-in amplifier to characterize it. I am now connecting it to one of the available signal input and output of the SHFLI lock-in amplifier. The SHFLI will generate the test tone and demodulate the resonator's response. Now we are ready to start. I have the Laban user interface running with the lock-in tab loaded, and it provides an overview of the experiment. And here we can set up our experiment by configuring the signal inputs and outputs, all the signal generators, demodulators, and more. Since we connected our resonator between the input and output of channel 1, we configure these two first, starting with enabling the output to generate the test tone. Now the next step is setting the input and output ranges to ensure they are optimal for the signals generated and the signals we measure. Now we want to work up to 8.5 GHz, which is why we connected our resonator to the SHFLI. As Paolo explained earlier, the SHFLI has an integrated frequency conversion. Therefore, we first set its center frequency to define where the 1 GHz measurement window will be located. As the second step, configuring the oscillator frequency will define the final frequency at which the demodulator will work. This is also the frequency of the test signal generated at the signal output. We can now start the oscilloscope tool to look at the analog signal at the signal input in the time domain. This is useful for a quick overview of the signal properties and the resonator's response to the test signal. The oscilloscope can calculate the FFT to show the spectral components in this analog signal within the measurement window. Here we see the test tone and other possible spurious signals. This is useful to configure the demodulator, for instance, which is our next step. Here in this window, we see 8 demodulators represented by 8 corresponding rows. These demodulators can run in parallel to measure different frequencies or harmonics simultaneously. In this experiment, we will use the first one, and it's already set to work with the first oscillator we looked at previously. The final frequency is displayed for each demodulator in this column. We can also choose various signal sources for the demodulation, that is signal input 1 at the moment. The next step is to configure the low-pass filter's order and bandwidth. Finally, we can enable the demodulator to send the results to the computer at the defined data transfer rate. The Lab1 user interface offers many ways to display and record data for different use cases. The simplest way is to look at the values in the numeric tab. Here we see the amplitude and phase information captured from the enabled demodulator. We can use the plotter tool to look at the same signal as a time trace. It's possible to set the duration of this measurement and analyze the measurement data by looking at its distribution or statistics. This provides a quick overview of the signal quality in real time. Until now, we configured the signal inputs, outputs, and the demodulator to capture the resonator's response at a constant frequency. Now we are ready to sweep the frequency to characterize the resonator. We can conveniently set this measurement up in the sweeper tool, starting from the start and stop frequencies. We choose a frequency range from 3.2 to 8.5 GHz and start the sweep. This range is beyond the mentioned 1 GHz measurement window of the frequency conversion. However, the sweeper is capable of controlling the center frequency and the oscillator frequency automatically, enabling frequency response analysis in the entire frequency range of the instrument. The sweeper can also sweep other measurement parameters such as the test signal amplitude, a bias signal, and so on, becoming an invaluable tool to characterize the setup or the device under test. Once the sweep completes, we can narrow the sweep range to capture one of the resonances in high resolution, for example, the one at 3.7 GHz. Since the dual-phase demodulator measures the amplitude and phase simultaneously, we can see the phase delay at the resonance. The resonator at this condition behaves linearly, and we see an expected pi-half delay at the resonance. The user interface allows fitting the resonance and provides us with its resonance frequency, quality factor, bandwidth, or phase delay at the resonance. This information is crucial to understand the device properties and designing closed-loop controllers if needed. With this, we will end the demonstration. We looked at configuring the instrument to prepare it for measurement. We can also use the oscilloscope to study analog signals and use different data visualization tools to capture the demodulated signals. The flexibility coming from this toolset streamlines the setup configuration. Then we perform the frequency response analysis on a microwave resonator to characterize its response over a wide frequency range. We can conveniently fit the resonances in the user interface to derive the most important parameters. I hope this demonstration gave you further insights into what these instruments enable and inspire you with new ideas for your work. Now we can continue with the next Q&A section. We are looking forward to hearing your questions.